Okay, I'm going back to chapter 5 in the Tochi book. As you probably guess, I go back and forth between these books here quite a bit. But this particular chapter is we're going to be looking at, we're changing completely around, and we're going to be looking at flip-flops and looking at moving into what we call sequential logic, or where things change with time. So we're going to be looking at counters, memory, various things. We'll be talking about finite state machines, and this will probably almost take us to the end of the semester by the time we get done with our finite state machine discussion. That's there. So we have quite a few topics to talk to out there, and difference between synchronous and asynchronous, major difference between serial and parallel transfers. We'll talk about edge trigger flip-flops, Schmidt triggers. I'll probably skip the Schmidt trigger, to be honest with you. Clock slew on synchronous troubleshoot. We won't get into troubleshooting, obviously. And sequential with PLDs. Again, that's the only way we've been doing things up there. And I will have a short little introduction to HDL. Before I get started, I wanted to schedule a lab for today. Unfortunately, the lab room is in use there. So Tuesday, I've already reserved the lab. So Tuesday we meet, as I recall, what is it, 8 to 10? So 8 o'clock sharp in the lab, and I'll be here at 8 o'clock. As I mentioned, Tuesdays we're going to start at 8 o'clock, and this week I did something I haven't done since I've been here. I blocked the door after the start of class, and I am just going to make that kind of lectures I could care less about. If you miss part of the lecture, especially when I'm recording it, you can pick it up, go back, watch the recording, get the notes from your friends. But if I have a lab where I go through the instructions for 15, 20 minutes and then turn people loose on the lab, and somebody walks in 15, 20 minutes into the class period, I've already gone through the introduction. I'm not going to do it a second time. So I just kind of make it a point that on lab days where I have to go through and explain how to do the lab, I'm not going to repeat that. So, and I had a situation where the class started at 10:15. I actually didn't start till like 10:20, 10:25, and at a quarter to 11 or 10 to 11, about half the class shows up and wants to come in. And I had already finished the discussion, so I just said no, not there. Okay, let me just kind of get through here. Structural level circuits from components. We've already done some of these things here, but that's there. Okay, block level of general, that there. What we've got here is, this is kind of a basic block diagram of where we've got on the left-hand side, everything we've talked about has been combinational logic. It has no memory. The output is strictly a function of the current input. The previous output has no bearing on what's going on. From here on out, we're going to have memory, and our memory, in the case of flip-flops and that, is what is our current state. You know, our output is a function strictly of the input. From here on out, we're going to be looking at circuits that our output is a function of not only the current input, but the previous state in which the system was in, right there. And we're going to end our discussion with a talk about finite state machines, where we actually define states and how we transition from one state to another. That's there. But there. So we're going to start off here. Oh, right there. Introduction. Okay, the flip-flop is the most important memory element as far as what we're doing. That's there. And typically we're going to be looking at a number of flip-flops. They're called latches, bistable, multi-vibrators, all kinds of terms. Typically, when we look at a flip-flop, we've got about 4 different types that we're going to go through. And I'm hoping these set of slides goes through all 4 in the order that they're supposed to go through them. That there. So let me. Yeah. Okay. Right there. So the simplest one is called an SR flip-flop. It's made out of nothing but NAND gates. Right there. So there. And I did lie to you a few minutes ago. I just now remembered that I will have to go back and cover 1 or 2 topics from combinational, but I'll do that just before the final. That's there. And the reason I want to do that is because there's some questions on the final that I want to make sure that I think I kind of skipped over them when I cover the material. And I'm deliberately waiting and going to cover them just before the final. That's there. So, all right, getting back to this particular circuit here. We've got two inputs here. And as we look at this circuit right here, we have to assume that if we put a 1 here, that's there, the output of this is forced to a 0. That is going to then force this input to a 0, which is going to force a 1 out. Okay, force a 1 out here. If I turn right around and if I put a 1, 1, we got a situation where things that there, in other words, what's going on here? Right here, we call this Q and Q naught right there. So now these inputs are active low, so an output will change this pulse right there. So when the latch is set, Q is 1, Q right there. So when we set them both at there, now if okay, at there. So what we've got here in this particular case, if this is already a 1 right there, that is going to put this to be a 1 here, and this is a 1, that's going to 0 and keep that a 1. So in other words, as long as these are both high, whatever state it's in, it's going to remain in that state right there. So these are active low inputs right there. So as you look at this right here, let me go through this again. We assume that that at this point that this output Q is a 0. If this is a 0 right there, and this is a 1, and this is a 1 right there. If that is a 0, that puts a 0 here, and that's going to put a 1 here, which puts a 1 here, and which keeps the 0 there. If we assume that this is a 1 and this is a 0, the opposite occurs. This is 1, this is a 0 coming in, that's going to keep that 1 there. This is a 1, that's going to put a 1 there, this is a 1, that's going to keep this 0 here. So it keeps the state. As long as both these are 1, S is 1 and R is a 1, as long as they're both 1, the output will not change, whatever it is. That's there. Now, if we pulse one of them low, right here, now in this particular case here, is we set that their Q is 0, and we take this low, that's going to push this to be a 1 right there. As soon as that pushes this to be a 1, that pushes that to be a 1. That's going to push this to be back to a 0 right there, which is going to then keep this as a 1 right there. So it's going to go from low to high right there. Now, if it's already high, it doesn't change. So here's this. So what we've got is we've got a circuit with two NAND gates that will remember the state there and we can pulse it and force the output high by pulsing the set. All it takes is a short little pulse, and the output goes from a 0 to a 1, and it stays 1 until it sees a pulse on the reset. So we've got a set reset flip-flop is what we call this right there. And it's a fairly straightforward circuit. All it takes is 2 NAND gates, and it will keep that particular output that there. This is in both cases Q ends up high that there. In other words, that there. Now when we pulse it low, the opposite happens. If this is low right here, that's fine. This is a 0. This is a 0. That's a 1. That puts a 1 here. That keeps it as a 0. So the output doesn't change right there. But here we put a 0 here, and if this is a 1, this 0 here is going to force this to be a 0, which is going to force this to be a 0 and change that to a 0. So the output will go from high to low. And also notice that the Q naught also changes in both cases right there. So when this output goes high, the Q naught line goes low. So they're reversed. So we've now got a circuit which now has a memory component to it. We could pulse it high, and it will stay high as long as power is applied to the system. And it will stay low as long as power is applied to the system if the output is low. So we can set it or reset it. So this is called an SR flip-flop. We can change its state by pulsing one of the two inputs. There are other SR flip-flops that use active high pulses. That's there. So this is the basic SR flip-flop. It's the building block of the rest of the flip-flops we're going to talk about today. That's there. So we could do the same thing with a NAND gate right there, where the only thing we do with the NAND gate actually is we just reverse the S and the R right there, and it actually does the same thing right there. Equivalent block diagram right there. So, and incidentally, this is another way of showing the NAND gate. That's one of the things I need to go back and review is the alternate representations right there. Right there. So, get there. Summary of the NAND latch is basically if set is equal to 1, reset is equal to 1, output doesn't change. If set is equal to 0 and reset is equal to 1, the output will go high and the Q dot will go low. We're setting the latch. If we take them both low, right there, if we set is equal to 0 and reset is equal to 0, I think this is probably wrong. No. That they're actually, this here, this discussion is trying to make the point is that this is a mistake here. This should be a 1 here. That's a mistake on the slide right there. Here's that if the set is 1 and reset is 0, Q will go low and remain there even after reset returns high right there. So that's just a mistake in the slide there. If we have the state of 0, 0, that's an illegal condition. And you don't know what's going to happen. Because if you go 0, 0, going back to this circuit right here, if you go 0, 0, that's going to try to push this one to a 1, and this one is 1, so it's going to put 1, 1 actually on the output is what it's, because you got 0, 1, that's going to be a 1 here, and that's going to be a 1 here, so you'll get 1, 1 on the output, is what you're going to get, and that's actually considered a illegal state. Let me just draw it. We'll assume that it's in the state 1, 0 at this point, and we put 0 here and 0 here, right? If we put 0 here, that's going to put a 1 here. If we put a 0 here, that's going to be a 1, 0, that's going to be a 1 here. Because remember that for this to be low, both in, and actually we've got, let me get this straight here. When we put this as 0 and this is a 1, that's going to give me a 1 out here. Well, if that's a 0, that's going to be if they're both 0s, it's going to want to put 1s on both of them right there. There's no choice there. It has, because if I look at the logic table for a NAND gate, A, B, X, it's going to be 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1. Excuse me, this is right there. The only place these are all 1s right there. Yeah, this is the only 0 right here. You can tell this is the end of a 18-hour lecture week, so my mind is getting a little drifted here. Let me go back through that there. I know you guys get that at the end of finals week, right? Let me just go through this truth table one more time and make sure I get it right, and then I'm going to leave it alone. A, B. This is a simple NAND gate. A NAND gate is only, the output is valid only when both inputs are, this is going to be low only when both inputs are high, and it's going to be high anywhere else, right? So if I put 0, 0 here, both outputs have to be high. That's the only thing you can have there. So going back to the slide here, this discussion here, it says if they're both here, tries to set and clear the latch at the same time, produces Q equals Q naught equals 1. So that's what I came up with right there. So that agrees with what I just did up there. And by definition, Q is supposed to be equal to Q naught, right? And Q, right there, I mean, Q is supposed to be the opposite of Q naught, so I can't have them both be 1. That beats the definition, so it's not an allowable state. Right there, the state, the input 0, 0 is not allowed. Right there, that's just by def. Otherwise, it's not going to operate as an SR flip-flop. Right there. So, right there, the cross NOR can be used the same. It's the same basic thing. Now, notice here the truth table. Right here. I will expect you to know that truth table. Right there. And notice that the way that we write the truth table here, that there, is that, and I'm not sure this truth table is right. The truth table is right. So this is the cross NOR similar, but the Q and the Q naughts are reversed right there. Right there. Again, that's the same thing, except for this one here is showing set 1 at there. Right there. This is an active high. This one is active high. They don't give the truth. They don't give the actual truth table for this one here. But let me go back here and make sure I've got this straight here. This is an active high right there. Point this out. This is active high. But what I want you to look at is the format of how the truth table is done. Set 1, 0, 0, no change. Now, if we go back to our other one, 0, 0 is our invalid state. That there. So this is set is equal to 0. In other words, that there, Q is equal to 1. In our other table, it would be Q is equal to 0. If set is equal to 1, reset is equal to 0, then Q would go to 0. That there. These are reversed right there. These inputs are reversed right there. These inputs are reversed, and the outputs are reversed right there. When you have 0, 1, 1 as an input, you get 0, 0 out. So you've got two different, they're both called SRs, but they operate differently. One's an active high, one's an active low. Right there. So let's make sure that this is the NOR circuit. The other one we had was the NAND circuit right there. So we have two different circuits that we're talking about here. We don't have the truth table for the NAND circuit. The NAND circuit is active low. The NOR circuit right here is active high. So they're both called SR flip-flops, but they're two totally different circuits right there. The NAND gate uses active low. That's when we went through in more detail. This particular, and the reason that in the NOR, and I'm used to doing the NOR first. That's why I'm a little off kilter here. But again, this is active high. It operates the same way, but this is looking for a pulse here to set Q high. A pulse here will set Q naught high. So these are set and reset are active high, and the output will change when an impulse is pulse high. The first one is active low right there. Right there. This circuit here is a active low right there. So we've got two different versions of the SR flip-flop right there. One is the NAND, which uses active low, and then the NOR, which is active high. That there. So the NOR, which is our active high, when set and reset are both equal to 0, it's normal resting state, nothing happens. When set is 1, Q goes high and Q naught goes low, right there, and it remains there even after set goes low. In other words, all we have to do is pulse it. If we do the other way, we clear it, we reset it, and if we put 1, 1, it puts Q and Q naught both to 0, right there. The output is in that there, and that's an illegal state, right there. So that's our SR flip-flop. There's 2 versions of it. Right there. And right there. So you just basically have to remember which one's the NAND, it's the active low, the NOR is the active high. Right there. And the SR is not used a great deal by itself, but it is used for a number of functions right there. So again, when powers, this is true for all flip-flops, you don't know their state. Normally, if you have a circuit with flip-flops, you normally will have a power on reset circuit that will reset them to a known state. Right there. So if set and reset inputs are in their active state, that's there. So to start, it must be placed in a state by momentarily activating it to start operation. Usually, like I said, a power on reset. The most common power on reset is here's your power switch, here's a resistor, here's a capacitor. When you first power it on, this goes to your reset. That capacitor, it looks like a short, and then as the voltage ramps up on the capacitor, it then becomes a high. Once it reaches 3 volts, it's a high, and then at there, this creates an active low reset right there. And we'll see that most of our resets are active low right there. So again, this is just simply a case where you toggle back and forth right there. And we're not troubleshooting this circuit right there. I'm just skipping through that there. Okay, some definitions here. Visual pulse. Right there. The width of the pulse is the time between 50% and 50%. And the rise time is between 10% and 90%. Right there. That is, signals that switch between active and inactive are called pulse waveforms, and that's just definition. You got two terms right here, 3 terms: time rise, time fall, and times width, the width of the pulse. Now, if we're looking at a periodic signal, we may have also something called duty cycle. And a duty cycle is defined by, if I have a pulse like here, right here, and we'll say that this is 10 milliseconds and this is 1 millisecond. It's going to be 1 millisecond over 10 milliseconds times 100%. So this is a 10% duty cycle right there. If I have a pulse rate that looks like this, and this is, we'll say, 10 milliseconds, and from here to here, and from here to here is 2.5 milliseconds, that's a 25% duty cycle. So the duty cycle could go anywhere from 0%, which is straight off, to 100% that's straight on. You could have a 90% duty cycle, which means that it's high until 9 milliseconds right there. So we've got, that's another parameter to look at there, is we can also look at, that's for a periodic waveform. That's there. And quite often when we're trying to do things like motor control, we'll vary the duty cycle in order to control how much power we turn on a motor or a light or a, any type of device. The Megatron on a microwave oven, if you want 90%, you would give it 90% duty cycle going to the Megatron. If you want 100%, you turn it on 100%. If you want 10% power, it'd only be on 10% of the time. And you would vary the pulse width. And that's easily done with a microprocessor timer circuit out there. So we also have the same definitions for our negative going pulse right there. This one doesn't show the pulse width, but again, we've got our leading and trailing edges right there. Actual circuits, it takes time for the pulse to change from one level or another. In other words, basically, nothing happens instantly, right? Nothing happens immediately in the electronics world. Because there's capacitance on the board, there's resistance on the board. And if I take a pulse like this and put it through an RC circuit like this right there, it's, this pulse that looks like this on this end is going to look like this right there. And that's what causes it, is that you have stray capacitance to ground, plus you have the resistance of the leads and the solder connections and everything else, so you get this effect here. In reality, it looks more like a exponential curve than it does the straight line. It looks more like an exponential curve if you look at it up there. Matter of fact, I've seen them where this one looks like more like this here, like that there. But the time definitions are still 90, 10, and 50. Rise times are the rise and fall times based between 10 and 90%, and the pulse width is based on the 50 to 50% right there. 50% to 50%. Rise time from 10% to 90%. Fall time from 90% down to 10%. Right there. These are just definitions right there. Again, and we have our duration right there. Right there. Okay. Here is an important concept. I will say it right off the bat that I've got 5 questions on the final exam. I've written the final exam. It's been vented and been passed on through. I can tell you that the format is 5 questions. You have to answer all 5 questions. It's not the normal 4 or 5 and you pick 4. You have to answer all 5. And one of the questions for some of you might be is, what's the advantages and disadvantages of synchronous versus asynchronous circuits? Right there. I like to put at least one question one part of every question where I make you think. Tell me why you do something. Why do we use hexadecimal numbers? Why do we use binary numbers? Those types of questions I like to ask. The reason I like to ask those questions is because it gets to you understand the material versus just memorizing things. So if I ask why do we use hexadecimal numbers, you can explain to me because binary numbers are too long to write out, but computers use binary numbers, so that's the easiest thing to use, but it's a shorthand way of writing that we can easily convert back and forth. I mean, you understand the reasons for it. The reasons are more important from an engineering standpoint than sometimes the actual process. And the reason is because the logic to why we do something doesn't change. The process changes as technology evolves. That's there. I looked at some previous test questions and they had people design counters using Karnaugh maps. Nobody designs counters using Karnaugh maps. We use an HDL to design a counter today. This class we don't cover HDLs, but why do we use synchronous versus asynchronous? That's there. So, first off, an asynchronous system, the outputs can change state at any time the inputs change. You have outputs that change any time they want. I can tell you right off the bat, bad news. You do not want synchronous systems in most cases. Synchronous systems may be simpler, they may look easier, but they will come back and tear you apart in some situations. Right there. So synchronous simply means that outputs can change at any time the input changes. Combinational logic circuits are all synchronous or asynchronous. You change the inputs, the output changes. You change the inputs, the output changes. Right there. Synchronous systems can only change state at a specific time in the clock cycle. Synchronous systems will change state either on a rising or falling clock edge. That's the only time they change state. Right there. They cannot change any other time. Right there. So synchronous systems, and the advantage of a synchronous system is because if everything changes at one time, all the inputs and outputs from the previous change have all settled down, and you know what they are. Synchronous, an asynchronous system, things are changing all over the time, and sometimes things change when they're not supposed to change. You have all kinds of things happening at the wrong time. And we saw that a little bit when we did the Boolean circuits using Altera, where we saw illegal outputs where there's glitches. That's there. And the reason is there's propagation delays through the gates, right? We talked about propagation delay. You know, that's where here's the input and the output varies by this propagation delay time. Right there. We talked about with adders why we use look ahead in order to get away from that, you know, this time that things are wrong. By having a system that only changes on rising clock edges, you will have a rising clock edge, and then one propagation delay later, you have the output. Then you wait for the next rising clock edge, and then you change state again. So you only do things on rising or trailing clock edges, right there. The clock is a rectangular pulse train or square wave, right there. Positive going transition. That there, I use the term leading edge. That there is positive going transition, the leading edge of the clock. Negative going transition goes from low, right there. So this particular author uses the term positive going transition, negative going transition. 99% of engineers use the term leading edge and trailing edge or falling edge, right there. So these are the edges. That's when things happen in a synchronous system, right there. So a clock flip-flop, there, we will show this little triangle. See the triangle there? Now, if the triangle is without the bubble, it's a leading edge flip-flop. If it's with a bubble, it's a falling edge flip-flop. So all these inputs are stable, right there. They're all nice and stable. This hits the leading edge, the output changes. And then, of course, we assume that these outputs are feeding other flip-flops down the road. That's there. And feeding other outputs. So we have more than one flip-flop in our system. So this signal goes out, and that feeds other flip-flops in our system. And we'll see these circuits. It has time to settle down before the next clock edge. Because remember, it takes time from this clock edge before this output becomes stable. That's there. So we don't change anything until the next, and all flip-flops in the system change at the same time. That's a key thing with a synchronous system. We have a global clock that everything changes simultaneously. That's there. So we have some setup time is the minimum time interval before the clock transition. That basically means that this is a parameter within the IC that simply says that our inputs have to be stable at least this long before we hit the clock edge. That's there. We have a series of inputs that go into our flip-flops. They have to be stable before the clock edge comes. These cannot be changing while the clock is transitioning. Otherwise, your results are not predictable. For things to work right, all your outputs from all your flip-flops and all your inputs from everywhere that's going to control this system have to be fixed and stable at least this long, our setup time, before the clock edge hits the flip-flop. Right there. Once they're stable, then we can hit that there and then transition to the next state. Right there. So again, this is the same thing with our synchronous control input. That there, the whole time in which the active transition needs to be kept. In other words, this is actually a clock input. In other words, this has to be held there for so long after the clock edge. All we're trying to say here is that we have some data is changing right here. Here's a bunch of inputs to our flip-flops. Here they all change, and they have to change here, and then here's our clock edge. We don't allow any change from this time to this time. Right here. Our setup time, and then our hold time. We have a period of time before the clock edge. That's called our setup time. All of our inputs have to be stable and fixed. We hit our clock edge, and then we have a period of time after our clock edge that the same inputs have to be held. So here's our clock edge right here. Our inputs have to be stable this time. Nothing can change during that time. Right there. We have a short period before, TS, and a short period afterwards. Right there. And that's just part of the design process, is that there. You know, as long as we're using inputs that are coming from from within the system, that's not a problem. Flip-flop the outputs are fine. The cues are feeding others. They're going through gates and everything's fine. That's there. Sometimes we may have to latch some inputs that are coming from the outside world. Right there. So we go back to the SR flip-flop, and we can have what's called a clock SR flip-flop. Clock is a trigger that causes the inputs to change. Is that there? Right here. You know, again, this is the same thing, only we've added another input right here. And this is a positive edge going that there. And this happens to be by the way, this happens to be the NOR gate, so this is active high. I should point that out real quick as we look at this particular truth table. And this is really the way you would normally write the truth table on clock flip-flops. We would say S and R are 0, 0 on a rising clock edge. Q is equal to Q0. Q0 means Q before the clock edge. That there, no change. If S is 1 and 0 is, or R is 0, the output Q goes to 1. If S is 0, R is 1, the output goes to 0. And if they're both 1, ambiguous, illegal state. So this is the most common way you would write the truth table, right there. Now, here's some truth table equations here. Now note that we only look at the rising clock edges when we determine what the output's going to do. We're only looking at the rising clock edges. Right there. In this particular case, 0, 0 no change, right there. Here on this rising clock edge, S is 1, so our output goes to 1. On this rising clock edge, the reset is high and the S is 0. The output goes to 0. Q goes to 0. Here the set is high, the output goes high. Here the set is still high, reset's still low, it still stays high. It doesn't change. So this is what we would expect to see on a clock flip-flop, and hopefully I'll come up with a lab for Tuesday where we can start putting this through on Altera. We'll probably only see it in simulation. We probably won't try to do it on the board, trying to do that there, because the clock that's on that board is so fast that it'd be very tough to see. Right there. And see, yeah, we have switches. We don't have. Yeah, we have some push buttons. Our lab is Tuesday, right? Yeah, Tuesday at 12 o'clock, 12:15. Yeah. So I have a class from 10 to 12, and I have intra meetings all day. Unless I can get something worked out over the weekend, I probably won't have time to do something in hardware, but we'll at least come up with a circuit that we can do in software. That's there. Okay. Again, this is the same thing. This particular one is, again, this is still a what I want to say, active high, right there, because our 1-1 is ambiguous, right there. That there. The only thing is now we're looking at the trailing edge, right there. So this is actually where these edge detectors come from, right there. I don't really worry so much about this circuit. That's built into the flip-flop right there. So, and I should point out that normally when we call something a flip-flop, it's going to be an edge trigger device. If we call it a latch, it's usually not clocked, right there. It's not edge triggered, right there. And again, I'm not too worried about the edge trigger right there. See, basically these are how you create that. And again, it relies on the propagation delay right here going into this AND gate is how it's created. And this does the same thing to create this creates the positive going, this creates the negative going right there. Right there. So that's how it's done. And again, you should note that the time is very short, 2 to 5 nanoseconds. So that setup time and that hold time is in that range too. So you're not talking about these inputs have to be stable for very long. Okay, probably the most popular flip-flop, and how am I doing on time? It looks like I'm plenty under the time limit. It's only 1:10 now. I got at least another 20 minutes I can talk. Okay. The JK flip-flop is the most common flip-flop out there. There's other flip-flops right there. However, it does have an interesting state, and one is that we can either set it, clear it, or toggle it. We have a new method there. So when we look at it right here, more versatile, has no ambiguous states, has ability to do everything the SR does, plus operate in a toggle mode. The JK flip-flop looks like this right here. It's JK. This is that there. This is the truth table for the JK flip-flop. Know it. Right there. That there. JK flip-flop, 0, 0. You hit a rising clock edge, the output doesn't change, just as the SR. If the J is high and the K is low, it hits a rising clock edge, it's set. If the J is low and the K is high, then it's going to reset. If they're both 1, they toggle. If it was a 1, it's now a 0. If it's a 0, it's a 1. So it does a toggling operation right there. So again, we're looking at this right here. It's a very similar type truth table. Again, we're only looking at these points in time right here. At this point in time, K is high and J is low, so it's going to reset right there. Here, they're both high, so it doesn't set, but it toggles. So it was low, it goes high. If it happened to have been high, it would go low. So this is a toggle state right there. Next rising clock edge, they're both low, so it's no change. This one here, J is high, K is low, so it goes to a set mode. Well, it's already set, so it's going to stay set. Here, they're both high, so it's high, so it's going to go low. It toggles here. Here, they're both still high, so it toggles again, right there. So this type of slide, I can't stress enough, right there. This is one of these lectures that there's probably at least 1 out of the 5 test questions is probably about 50% going to come out of this lecture. I don't know how many times I can give hints on that without there. So there's a lot of the, this is the basic definition of flip-flops and how they work. In synchronous and asynchronous circuits, or asynchronous versus synchronous circuits, there's a lot of material in this particular set of slides that is core there. So the clock that reflects, again, this is the same thing. Nothing changes here except for this, notice, is going down. This truth table shows it going up. Again, that there. And again, the D flip-flop, again, I'm not worried about the internal circuitry. All these slides on the internal circuitry, don't study. Don't worry about that there. So the internal circuitry is not important right there. But these timing there in truth tables are. Okay, the D flip-flop is one that there may be implemented by time JK through an inverter, used for parallel data. D flip-flops are a very commonly used thing for shift registers, and we'll talk about shift registers. That's there, because shift registers are a very common thing in converting serial to parallel data. We shift the data in a serial fashion and then latch it out in parallel, or we set all the D flip-flops in parallel and then shift our data out in a serial fashion. So we use shift registers, which use a D flip-flop. And a D flip-flop is all it is like a buffer that only changes on a rising or trailing clock edge. You only look again at here. And whatever D is at that particular point in time, D is 0, so the output goes to 0. D is 1, the output goes to 1. So, and what have we got this in hand mode? How? Okay, because that's screen there. So all we're doing is we're looking at D, and whatever D is, the output goes to on the clock edge. A place where you're going to see that might be, for example, an address latch decoder, or address latch, where we have a signal that's going to latch data. We've got something coming from an A to D, and the output's valid. We want to latch that data so that the processor can read it. So D flip-flops are used for a lot of latches right there. So again, we have the negative trigger implemented by applying a single inverter, or the edge trigger D flip-flop. All we're doing is we're ensuring that these two are not equal to each other. So if D is 1, then J is high, it's going to set the output. If D is 0, then K is 1 and J is 0. So this simply generates a D flip-flop from a JK flip-flop. That's why the JK flip-flop is such an important one. And then there's another one not talked about in these slides. It's called a toggle flip-flop, which just simply ties JK to 1. Right there. And all that does is toggle every time the clock is set there. So, okay, parallel data transfer. This is again what we're looking at here, using D flip-flops. All we're going to do is we're going to latch the data at this point, and then it's going to be read out at a later point in time, right there. So, that's there. This example, all 3 bits are transferred simultaneously. So we latch this data at a particular point in time. That is important. For one example is, let's say you want to sample music. We talked about music being sampled at 44 kilohertz early in the session. That's there. So 44,000 times a second. You want to latch that music. That's the output of the A to D. That's there. And you want to latch all 24 bits of your music, if it's CD quality sound, at the same time. And you want to get it at exactly that time. You would use this type of latch to grab that data so that you know that you get it when you want it, right there. Because remember, if this is coming from A to D, it might be changing with time. That there. So we grab this data all at the same time. That there. So we get, the key word is transfer simultaneously, and we not only simultaneously, but we can control the sampling rate, how fast or how often we grab this data. Again, it uses edge trigger to ensure only on the active. Edge trigger is not used as a result. It's called a D-latch. If we don't use the edge trigger, then it's going to latch data, and the output will change however it wants until the latch goes low. Right there. And it looks like this right here. But notice the one thing that's missing is the little clock symbol. This particular circuit, the output's going to change whenever the input changes as long as the enable is high. There's no leading edge or trailing edge restriction. Right there. That there. And again, I'm not. Okay. You can have, and almost all clock flip-flops do have some asynchronous inputs. The 2 that are normally found are the preset and the clears. Those are used to set and clear the flip-flops at power up, or in the case of a latch, in order to, that they're active low. Asynchronous inputs have a bar over the labels and inversion bubbles. That's all that they're. Asynchronous are not used. They're tied to their inactive state. In other words, most asynchronous inputs are going to be active low. Most are active low. This is an example of a JK flip-flop with a preset knot and a clear knot right here. And when we look at this here, we are going to assume that this is the normal operation right here. This is normal operation right here. If, and I don't know what this, this basically means that we don't care about the clock right there. So if the clock is done on a transition, Q does not change, is all this line says. This only changes on that there. However, if the preset is tied to low, excuse me, right here, let me go through this truth table again. That there. I think I kind of went offside. This is normal operation. Normal. Right there. Normal operation, just like we saw before. This line right here is just defining that there is no clock edge any other time. That's there. It should just simply say not a clock edge right there. We don't care what JK are. we don't care, as long as the preset and the clear are both high, the output's not going to change. That's all that says. The only time it changes is that they're. However, if we take the clear low, then we're going to take the flip-flop low. If we take the preset low, we're going to set the flip-flop, regardless of what the clock does. Regardless of what the clock does. We ignore the clock. And this state here is invalid, right there. So this is a JK flip-flop. These are used for a lot of different circuits right there. And we're going to see some circuits on the using that there. So, okay, this is just some discussion. You know, I went through these slides. I should have deleted some of them. They just basically talk about the fact that you normally see preset and clear, so that you can tell them from set and reset, but at there, sometimes you see labels such as SD and RD for direct reset at there. I've always seen preset not, pre and clear not. It's the two I see. Normally I see this and this. That's what I see. Right there. Just like you see there. That's the normal way of operation right there. So what this is saying here is we've tied J and K high. So what we've done here when we tie J and K high is we've actually created a toggle right there. This toggles on the active low pulses right there. However, this right here is going to force it high at that point, regardless of what the clock is doing. Here, we're toggling at this clock edge, we're toggling at this clock edge, we're toggling at this clock edge, we're not toggling at this clock edge. And the reason we're not toggling there is because our clear line is low. And as soon as our clear line went low, we went low, even though it was not a clock edge. And then we toggle again at this clock edge. And note that when we tie J and K both high, we create what's also called a T flip-flop. This book doesn't discuss the T flip-flop, but there is another one called the T flip-flop. You got the SR flip-flop, the JK flip-flop, the D flip-flop, and the T flip-flop. Let me write those down so that as you go through and look at the notes, you see them at least one point there. You've got the SR, the JK, the D, and the T. Those are the four types of flip-flops right there that we're concerned about right there. Okay, I think I'm going to probably get close. Let me see, where am I at on time? Right there. Oh, I'm only talking 58 minutes. I was late starting. I got to talk another 10, 15 minutes at least, right? We can't end too soon. We got a lot of material to cover. It's just my problem comes to be is that I don't want to cover too much in one day, but we don't have that many days, so I'm just going to keep barreling through till we get through some of this more here. Okay, we already talked about the setup and hold times right there. Propagation delay, time for the signal to be from the input before it, in the case of a flip-flop, it's the time of the clock transition till the outputs are valid. In the case of an AND gate or gate, it's the time that the inputs change till the outputs are valid or change right there. Maximum clock frequency that will give you reliable output. Now that's tied directly back to both the setup and hold times and the propagation delay. That's there. And the reason is that when we look at, and I'm afraid to write here, let me just kind of, that there. Here's your clock edge right here. And let's use a positive. Here's your clock edge. We know that things have to be settled somewhere before that and have to be settled somewhere after that there. Then after the clock edge here, at some point our outputs are all going to be settled right there. and that has to be before this next hold time. Right there. Because our propagation delay is we come in, here's our clock edge, right here, our clock edge. Here's our output. There's a time delay here between here and here, our propagation delay, right there. That's the amount of time it takes from our rising clock edge till our output is stable. And then we're assuming that these outputs are going to, and we'll take it right back to the same one for example case. This has got to be stable for so long before the next clock edge. So those two times added up has to be longer or less time than the next clock edge. So that goes right back to this, you get this maximum frequency, and those are really tied back to these two parameters right there. Right there. Our maximum clock frequency is actually a function of both our propagation delay and really our setup time. But in some cases also the hold time. Right there. So those all tie together. And also into that there is our pulse width and our minimum clock time between high and our rising and falling edge times, right there. And our asynchronous pulse width must be high before going low. This also has a minimum height width. This is a minimum width that an asynchronous clock has to be, signal has to be active before it's seen. I can't give it if I want to reset a flip-flop, I can't give it a half a nanosecond pulse. That pulse has to be a certain width, is what that says. This is also saying that our clock pulse has to have a certain on and off time. Now most clocks are 50% duty cycle. So this parameter really doesn't come into play as much as this one here. Because when we say clocks are 50% duty cycle, means that they're on half the time and off half the time. So our maximum clock frequency will tell us, will be such that we meet the clock, the high-low times. But it's possible that you may not have you may have a 10% duty cycle clock. There's nothing that says you can't. Remember that things only change. Things only change on the clock edge, right? They only change here. So there's nothing that says you can't do this. Right? Is there? Because the only time we care about is here. But that parameter there says that we have to have a minimum time on right there. That's what this parameter right here says. Pulse width high and low time. Minimum clock time between high and low changes. So we have to have a time with low and a time with high. Because we could go the other way, and I don't know what OneNote does this, where our clock just pulses very short like that right there. That's our clock. And here's where our transitions if it's a positive going clock. But then we have this TW low that we have to meet right there. But again, 90% of the time you're going to be using a clock that's 50% duty cycle, so you can ignore that pulse width, high and low times. This actually becomes your big parameter that you should worry about along with this one here. Those are the two biggies that you should be concerned about. And let me just kind of throw something out here that's a little bit interesting, is if you're dealing with Altera devices, these are very stable. If you're dealing with an FPGA, which we have not talked much about in this class, such as Xilinx, that will route the circuits differently every time it routes a circuit, those could change from one compile to the next compile. That's what makes life very interesting when you're trying to push leading edge, is that you design your circuit in VHDL, or you use your schematic diagram, or you write Verilog, or you do a mix in between, however, and then you do a complete compile. It works great. You make a minor change, and all of a sudden, your maximum clocking frequency dropped 20%, and the circuit blows up in your face. Not literally blows up, but doesn't work right. That there. It can get quite frustrating. Not to say that I've never had that happen. You know, let's just say I've spent probably weeks on some of these problems. That there. And that was back. It was really interesting back when Xilinx took 6 hours to route. So you make a design change, you route it, you test the design, and it didn't work. You make some tweaks, you reroute it, went home for the night. The next morning, hopefully it worked again. You know, you only got two routes a day, and you know, nowadays the computers are a lot faster and that there. But back then we were operating on, you know, Pentium 4s or something like that. That there. So those are our major ones. And our clock transition times less than 50 nanoseconds. That's maximum time for a clock transition. That there. That's how long it takes for that there. Again, these clock transition times. Those are typically talking about discrete logic, not so much about programmable logic. That's there. But the big one is really that there, and that can be with Altera. It's very, very stable. I could probably look at a Cypress, or you know, a particular family, say Stratix, 4 family, and its maximum frequency is listed at 2 gigahertz. You know, that's there. And pretty much any design that I can fit in that part will run at 2 gigahertz. But if I take that same design and put it into a Xilinx part, some routes might operate at 3 gigahertz, some designs will only operate up to 1.5 gigahertz, depending on how it routes. Same circuit, but just depending on how it routed it. So these are just timing parameters. I'm not going to be testing a great deal other than these are what they are. Okay, flip-flop propagation delays, I've already talked about what those are. These are just graphics showing the same things as that slide showed. Right there. This is our pulse width up there. And you find these things all through on the data sheet. Right there. So in other words, this particular one, this is for a TTL part, or a CMOS part. And what you're seeing on this one here is, again, the biggie right here is that this will operate at 15 megahertz, this will operate at 30. LS is low power, high speed, right there. These are, the CMOS are much lower there on the C part. The high speed part is somewhere in between. That there. These are standard off-the-shelf components. Again, I don't get too excited because you can't even buy half these components anymore. That's why we're using Alteras for the lab. That there. I think I'm going to do the input of another voltage trigger by the same clock. That their propagation delay. This is what we're talking about when the output is connected to 1 by the same clock. You have a timing propagation. Again, that's usually not a problem because so most edge triggers have hold times right there. This is the key, is that the hold time is usually 0. After the clock edge, the data doesn't have to be there very long, if at all, is what this slide is saying. So if you have an older technology that does have a hold time, you can get it into a problem. Where you get into the problem is that the propagation delay is more than the hold time. That's where the problem comes into. You see, this is propagation delay right here, going from high to low. If this is greater than our hold time, then the inputs to the next flip-flop are changing before they're allowed to. But this slide here is saying point blank is most edge trigger flip-flops had hold times that are very, very short. 5 nanoseconds or less. You're not going to see propagation delays in discrete logic of less than 10 to 15 nanoseconds. That there. Even on the Altera parts, you're seeing about 9 nanoseconds. So if you got something less than 5 nanoseconds, you don't have a timing problem, as long as you're using that there. And I see people getting distracted, and I think I'm finally beyond where. How many more slides do I have left in this right there? I think I'm to the point that you hear they talk about that there. Why don't I stop at this point here? Because now we're going to get into the applications, and that's where things get a little bit more detailed. I'm going to stop at this point right here. Right there. And I'm a little shorter than normal, but